What's your first step?
And
then what?
Divide by 4.
Okay. So you have tangent squared x is 1/4. What do you? Yeah, solve. It's not solve for tangent. Do you think the algebra book writes in slang?
Yes.
I read it the same way you
Shimkey?
Oh, that's what I thought it was. I'm sorry. I thought it was that too.
This is bad.
Mr. Ruby, you read these from. I didn't know.
I to you.
What chapter?
I wrote that.
I get it, because he has imaginary
I root for you.
Oh, I got it.
I
Anyway, what do you do next?
Square root.
Okay. When you take a square root of an equal sign, what do you have to do? So you have the tangent of x is going to equal plus or minus 1/2. You okay with that?
Yes.
Which basically means what angle has a tangent of 1/2. Oh, excuse me, plus or minus. Now, when I throw in a tangent value with a plus minus, how many total angles am I going to be finding? Four. Good. What triangle gets me to the 1/2?
30, 60, 90.
Think about it. 1 root 3 and 2. Or 1 root 2. Which one of those gives you a 1/2 for a tangent value?
The top one.
You're thinking sine.
Wait, that should.
You don't have one in your special triangles. Which means, in this case, you have to use your calculator.
All right. I like calculating.
So we're looking at solving the equation between the intervals between 0 and 2 pi. Adios. See ya. Have a good weekend.
At least he can do it.
He started drawing all the circles and stuff, and he just.
Scared them off.
I turned my head.
I exactly.
Okay. So here's what happens. Guys, cut it out. Here's what happens. We have to start to think about what does it mean to, in terms of radian for 1/2. Well, if this is 0, oops. Let me redo this. If I'm at 0, this is pi over 2, pi, 3 pi over 2. Are we okay with that? If I inverse tangent this in radian mode, because it's asking me to be between 0 and 2 pi, it's going to give me some crummy decimal. I got to figure out where this crummy decimal is being placed. So let's think about decimal approximations for pi. What's pi? Okay.
4159265.
What's half of that?
Pi over 2.
1.57.
Wait, what did he say?
Pi over 2.
Wait, what is that?
What's happening?
Pi over 2.
I said we were figuring out what's half of pi. He said pi over 2. It says the girl in the honors algebra 2 class. So, and then you.
Right.
So if I add pi to this, I wind up at 471. And then if I finish out at 2 pi, I'm at 6.28. Are we okay with that? I'm just putting 2 decimals real quick to see an approximation where we're at. So in your calculator, since our interval was at between 0 and 2 pi, you have to make sure your mode is radian. So type in second tangent 0.5 of half. Yeah, because it told us to put our solution in between 0 and 2 pi, so we're going to be in radians here. So it's giving me a decimal equivalent of 0.46. You okay with that?
Yes.
0.46 is less than 1.57, so it's somewhere in the first quadrant. Are we okay with that?
Yes.
Also, remember, your calculator is going to find tangent between pi over 2, negative pi over 2. So this gives me my first positive angle. Where's my other positive angle for tangent? What quadrant?
4, 3.
Which is
3.
3. How do I get from here to here?
Add a pi.
You add a pi. Very good. Add a pi to 0.46.
Oh, and you get 3.6.
Good. So there's my other angle. In radian, 3.6. I type in the same thing, inverse tangent of negative 1/2. It gives me a negative 0.46, which means it's giving me the angle again into that fourth quadrant. But that's not between 0 and 2 pi, is it? It's just the reference angle. Which means to find that angle between 0 and 2 pi, I go the other way around. So all I have to do is take 2 pi and subtract 0.46. Was it 5.82? Are we okay with that? So there's my negative angle. And how do I get to that one? Subtract pi. So sometimes, if you don't get it to bounce into a triangle, you get to use your calculator. So if you see this question on a non-calculator portion of your test, will you be able to do it? No.
It's a riot.
We can riot like
Yeah.
pitchforks and flames.
Yeah,
And,
like all of that.
Like as far as we can go. Like
no,
check
basically
out-
what would happen, this part would be on a calculator part. Okay? Just to show you guys, you will see it from time to time where it doesn't bounce to a triangle, and if it doesn't bounce to a triangle, you need to use your calculator. Yes, ma'am. That's why we have 2 of each. Okay? So let me show you the other thing that happens when you have what are called general solutions. Shimke, this 5 isn't 5.3 secant squared, just so you know.
Okay, thank you.
Look, it was missing the
Solve
four.
4. I know, just, it's great. Yeah.
I don't know slangs.
It's awesome. Oh, I was leaving them. That was awesome. What do you do first?
Plus 4.
Then what?
Divided by 3. 3.
Now what? Good. I go plus minus. Secant is the inverse of what trig function? Cosine. Flip everything. If I inverse both sides, that's keeping everything, that keeps everything balanced. I get now cosine of x is plus or minus root 3 over 2. Since it's an inverse, since this is an inverse function, whenever you have an inverse function on one side and values on the other, you flip it, and that's how you go from it. It's a really nice, easy way to do this. So what angle has a cosine value of plus or minus root 3 over 2? And we're going to talk about this in terms of what's called a general solution. So what we do is we figure out all the angles. How many angles are we going to have here?
4.
There's going to be 4 of them. So we list out the 4 and look and see what happens. Root 3 over 2 is our 30/60. And it gives me which angle? 30. So the first angle that I worry about is going to be pi over 6. And since I'm going with all 4 angles of pi over 6, it means I have to go to every quadrant to bounce pi over 6. Second quadrant, up pi over 6 gives me what? Good. Third quadrant gives me, and fourth quadrant. So if this said list all possibles between 0 and 2 pi, you just did that. what makes this problem more specific is called as a general solution. General solutions want you to write down the minimalist possible. What's the least amount you can write down to show that you encompass all of the angles at work? So here's what happens. When I start at pi over 6, is it equidistant from here to here and then back again?
Yes.
No. If I go from here to here, and then I start from here all the way back, is that the same distance I'm going both ways?
No.
No.
Well played.
But if I start here, and I head here,
Yes.
and then I go back, isn't that just 1 pi each time?
Yes.
So if I say pi over 6 plus pi n, where n means the number of times I'm going back and forth, I will land on either this point or this point, which means I don't need to write down that one. Same thing goes for with the 5 pi over 6. If I start here, to 11 pi over 6 is a pi, and back again is another pi. I can tack on a pi, and I don't have to write that down. It's more of a shorthand, which basically stands when you do these problems, you pick whatever angle you're working with, and you try to see, is there another value that's going to allow you to get back to it with the same amount of revolution? If not, if it was, let's say if it was just the 2 values up top, if it happened to be just the 2 values here and here, if this was pi over 6, then I'd say, well, it'd have to be plus 2 pi n. If it was this one also, it would be at 5 pi over 6 plus 2 pi n. Because it takes that long to get back to the same spot. It takes that long to get back to the same spot. It works out really nice when they're directly across from one another, especially when you have plus minuses. Yes, sir?
What are we doing here? How is this relevant to 14.4?
It's solving the equation. It's another way of solving an equation. I'm throwing in here some more inverse functions, which we worked on, and solving the equations with inverses with what's called a general solution. Remember how we did coterminal angles?
Yeah, but
This encompasses all coterminal angles of that value.
wouldn't it make it harder if you get the ones where it's not perfectly straight or whatever? You might get the ones where they're at different angles.
Those are actually even easier.
They're easier?
Yeah, they are.
Wait, how?
Oh, I'll get there. I'll show you. Okay. Yes, sir.
Wait, so Avogadros is pi n and mine was 2 pi n.
There's your different problems. These two and back again are not the same distance because they're not across from one another. So to get from here back, I have to go around once. From here back, I have to go around once. Whereas when they're across from one another, it's just here, here. You're just oscillating back and forth real quick. That's all. Yeah.
Why can't we just say 7 pi over 6
Because it's encompassing all the other coterminal angles. And it's the only difference between general solution and with bracket is general solution has the pi n's or 2 pi n's or pi over 2 n's. It's just looking for the repetitions. You're labeling the repetition. They don't have to be. They don't have to be. I'll show you another one. Yeah, Martine.
So I get that like the n is the number of revolutions, but
Yeah.
is it like 1 pi or is it 2 pi? I don't understand why you would have the 2 pi n.
If you're starting here and the other point is here, these two, there's nothing that's equidistant to this spot that is a solution. So it means I have to go all the way around to get back to it. If you go all the way around, it's 2 pi.
Right, yeah.
If it's directly across, it's 1
So
pi.
you're trying to get to the opposite of it. So the number of revolutions would be per pi.
Right.
Right. So then why would you put 2 pi n?
If I go, it means that if I go around 1 time, 2 times, 3 times, every time I go around, if I go around 4 times, 1, 2, 3, 4, I'm back where I started.
Yeah.
If this was plus pi, if I go
Then
3
that's
times,
1 pi.
it'd be 1, 2, 3, and I'm not where I'm
Okay,
starting.
so the n, so it's basically making it an even
Yeah.
always. Okay, thanks.
Same deal here. Tangent squared equals cosine x plus tangent squared x. This is another style problem where we're going to set equal to 0, where we did stuff like this last time around by simplifying things via factoring, trying to see what we can get to take out. So if I have tangent squared equals cosine x plus, or times tangent squared, set one side equals 0, so I'm going to subtract the left and move it to the, or excuse me, subtract the right, move it to the left. So I get tangent squared x minus cosine x, tangent squared x. And what's the first rule of factoring? What do they have in common? Tangent squared. If you factor out a tangent squared, you get 1 minus cosine x. And now you're at the idea, yeah, right?
Couldn't you just subtract tangent squared x and move it up to 0 equals cosine x?
I can't because it's multiplied. It's the same idea as if you had this. You'd have to move it over and then factor.
Yeah.
Okay. Yes, sir.
Alright, so I'm probably missing out on some fundamentals of algebra here. Why can't you just divide the tangents out?
You eliminate a solution.
Go ahead. Okay.
You eliminate solutions, and then all of a sudden you're taking out a pair of 1. Whereas when you have upward polynomial stuff, you have to factor everything through. It's the same rules that applied when you had polynomial operations back in chapter 2.
Okay.
That was
Are you okay?
I don't remember what
You
chapter it
seemed
was.
a little sick there.
Yeah, exactly. Do I have 2 terms now that are set equal to 0? Set both equal to 0. And now you set yourself up with the inverse function.
I'm not setting myself up for the inverse function.
Why not? Don't you want to do a trick like this? This is fun.
Yeah.
Around and around we go. Where are we stop? Nobody knows. What's the square root of 0?
0.
So this one's pretty easy. You don't have to worry about plus, minus, or anything like that. So x is equal to the inverse tangent. What angle has tangent of 0? The other one's going to be what angle has the tangent, or excuse me, cosine value of 1. Well, subtract 1 and divide by 1. Divide by -1, you get 1. Okay. So now when you have zeros and ones, it means you have to worry about your quadrantals. So you have to remember, what does it mean? Well, on quadrantals, you have 1, 0, 0, 1, -1, 0, 0, -1. Tangent is what over what? Y over x. So I need to know where I can get y over x where the it's not going to be undefined. Where does that work? Y over x at 0, and pi. You okay with that? And where's cosine equal to 1? 0. There's 3 solutions, but one of them is replicated. It's got multiplicity.
Okay, we can still say that?
Now, does this 0 here, if I place here, and the other answer is here, going from here and back again. But that basically, if I write it out, here's where things can get kind of weird. Treat them as their own independent solution. Because if you tack on and say it's going to be 0 plus pi n for solution, that means that this is a solution here as well, doesn't it? But pi is not a solution for that. It's more of a pre-calc thing, but we'll worry about that later. So as you go from here to here and back again, does it just oscillate between the two? They're the same distance? For your answer. Don't worry about that other stuff next year. You guys can break out. You don't really need to worry about it right now. Because that's right, we're doing the same stuff in pre-calc. Or we just finished it. Pre-calc is all trig. The second semester of this. Yes, ma'am.
So where did one of those like tangents go? I don't understand where it went.
We took the square root of both sides.
No, but I don't understand how you went from
from here to here?
Here, no, yeah, like, I don't understand why the other tangent one.
Okay, if you look at it like this, this is x squared minus y times x equals, x squared equals 0.
Okay.
What do they have in common? Factor it
Oh,
out.
so you moved that, okay. Totally missed that. Thank you.
That's all it is. We were using the same rules for algebra for solving equations like we did all a long time ago. It just happens to have 3 letters instead of 1. Nasty 3 letters. 3 letters you probably shouldn't say on TV. Sure.
And no one understands.
No one
gets it.
No one under.
Oh my gosh,
Oh, I don't have. I accidentally closed it by mistake. Sine squared x plus, excuse me, sine squared x times cosine x equals 4 cosine. Once again, we're going to set it up in such a way to get one side equal to 0. Everybody okay with that? Do those guys have anything in common?
Cosine.
I'm going to factor out a cosine. Do I have 2 parts that are equal to each other? The blue part's right there. Yeah.
Wait.
You could, but there's no reason to because you're going to solve for x anyway. Because you're going to get the same solutions here.
Well, there's an X there.
Oh, sorry, did I forget that? I've been trying really hard to put the x's in when we're working equations.
Wait, no.
What?
You got it?
Who's Mr. Murphy?
Out. What did I say?
After the I, after the T.
You should correct it.
Brandon.
What is it?
Me fail English, that's not possible. So I have 2 parts to solve for 0.
Wait, let me see that. Wait,
Guys, worry about it later, okay? I guess we have plenty of stuff to finish out here. What angle has a cosine of 0? And then here, what angle has a sine of plus or minus 2? So what angle gives you a cosine of 0? What's the ordered pair at 0?
hang on, this is
What?
the ordered pair at 0?
What's the ordered pair at 0 degree?
I was following it all the way until we got to cosine x equals 0 and sine squared x minus 4 is equal to 0.
Do you have 2 terms both set equal to 0?
Yeah.
So you set both terms equal to 0?
Just like regular factoring?
Just like regular factoring.
What?
It's all the same thing.
Oh.
So cosine of 0 is going to be at pi over 2 and 3 pi over 2. What about sine of 2? There's not one. Remember, what was the parameter given to you by sine? Sine values are always between 1 and -1. So this is a no-go. So my solutions in terms of general, is pi over 2 and 3 pi over 2 equidistant going both directions?
Yes.
So I would write it as pi over 2 plus pi n.
What is the n signify?
Number of times. Number of times you go around.
Oh.
If I go around 5 times, I'm going to go 1 little, 2 little, 3 little spots, 4 little, 5 little, and I'll stop. And I'm still going to always get 0.
Oh my gosh.
Yes, ma'am.
I'm confused on how to go from x equals cosine negative 1 to pi over 2.
What angle has a cosine of 0?
Is that really
Okay. No, you don't have to draw a circle. I want to show you guys 2 ways of writing out interval. It'll say solve for the interval, 0 to 2 pi. That means list all possible angles. Or it might be written in terms of interval notation. Interval notation is brackets and soft brackets. Hard bracket, soft brackets. Hard bracket 0, soft bracket 2 pi means between inclusive 0, non-inclusive 2 pi. All right? Means the same thing, just so you guys see that. So if I want to solve the equation, solve for x here. There's really not a whole lot I can do as far as moving things left or right, because I have sines and cosines mixed together. But one of the things that I can do is I can square both sides. One minus cosine quantity squared means 1 minus cosine, 1 minus cosine. Foil out. Root 3 sine x, is there any addition in between the two? It's just a monomial. So it's just monomial times monomial. So what's root 3 times root 3? 3. Sine times sine? Now is where Pythagorean identities come into play. I'm always trying to forget my x.
Same.
Jokes don't get any funnier as we get closer to the end of the year. You guys start just keep going. Yeah. This is where it becomes important to use Pythagorean identity, because you have sines and cosines. I can rewrite sine squared as what?
Cosine
1 minus cosine squared. So I have 1 minus 2 cosine x plus cosine squared x equals 3 times the quantity 1 minus cosine squared x. You okay with that? Distribute. And I get that. We still okay. Set aside equal to 0. Basically, in this case, I'm going to move stuff on the right to the left, because I have a negative 3 cosine squared, and on the left I have a cosine squared. So the negative 3 loses. We'll pick up a little bit. So I'm going to add the 3 cosine squared. I'm going to subtract the 3. So let's see here. We get 1 minus 2 cosine x plus cosine squared x minus 3 plus 3 cosine squared. I'm just writing out longhand to show you guys what I'm doing. I'm going to put it all in descending order by combining like terms. What's cosine squared plus 3 cosine squared? 4 cosine squared x minus 2 cosine x. 1 minus 3? That's correct. At this point, I want you guys to see that it's nothing more than a quadratic equation. Everybody see that? Remember that little trick I showed you guys before called U substitution? Did I show you that?
No.
Okay. Use substitution. Use substitution is used a lot of times to make something that looks horribly complicated into something really easy. For example, I'm going to let u equal cosine of x. So I'm just going to substitute in, and I get the finally quadratic. 4u squared minus 2u minus 2 is 0. It just looks cleaner. It's easier to work with when things are cleaner. That's all. Does that make sense, what I did there? You don't have to do it that way. No, I just think it's easier because it's a very simple step to go back and forth within it. And it's easier, in my mind, to see less complicated work. So, Shimke, you said GCF, right? What's the GCF? 2. In a quadratic, if you're set equal to 0, if you take out a GCF, does it have any bearing upon the problem the rest of the way? No, because it's just a scalar. You can divide it out and it's gone, all right? So now I'm just going to look at the interior part. What times what's negative 2 you add together to get negative 1? Negative 2 and 1, good. So I get 2u squared minus 2u plus u minus 1. And then I group it. Okay? This is like everything you've learned in this class, so I'll put together in one problem. And then I basically, what's up? Special edition, special delivery. Thanks. Have a good weekend. What did you stand for again? You put it back in. Here, on.
Where did you get the minus 2?
What times what's negative 2 you add together to get negative 1?
Oh,
So I'm just going to rewrite my terms as 2 cosine x plus 1 and cosine x minus 1 equals 0. The only reason why I use this u substitution is that it just makes the problem less cumbersome. Less writing things out. That's all. There's the only reason why I do that. You don't have to. It doesn't make any difference at all. I just think it's easier to work with when you don't see as much information. Does that make sense why I do it that way?
Yeah.
So now it's a matter of subtract 1, divide by 2. What angle has a cosine of negative 1/2? And what angle has a cosine of 1? There's a lot on this one. Okay. So, what triangle gives you the 1/2s? Which one of those gives me the cosine of 1/2?
None.
The 60, but it's negative, so it's going to be in which quadrant? Second and third. 60 degrees is pi over 3. If I go up pi over 3, where am I at?
2 pi.
Yep. 2 pi over 3. If I move downward 2 pi over 3 for the third quadrant, I'm at? And then cosine value of 1 is at 0. None of those are equidistant from either one of them. Okay? None of them are. So each one of these solutions, oh wait, I'm sorry. This was an interval problem, wasn't it? I don't have to do pi ends. Done. 3 answers.
Did you say move?
Okay? I didn't have to list them out. If it didn't have the interval, I would have to tack on a 2 pi n to each one of them. Yeah.
Doesn't that have to be negative?
No, because we're going between 0 and 2 pi.
0 is the third answer.
Yeah. Okay. Try these. Do these, but I want you to do these as general, okay? Do these as general solution. It's 860. It's 14, 4, 860. I want you to try those 10 with general solutions, okay? Can I have the eraser, please?
Nice catch.
Hey, see how I caught it so it wouldn't get the marker? Okay. Oh wait, I can't do this. I'm not allowed to. Martine's job.
Martine, come on.
What numbers? Yeah, Tara gets on him again. She's like, did you do it today? He's like, yes, Tara. I don't know what I do. I don't know.